how many numbers are there?
Yeah.
It's,
Yes.
it's one of those questions that seems simple at first.
Most people would just say infinite and leave it at that.
Exactly. Just one big, endless concept. But in the late 19th century, one mathematician, George Cantor, came along with an answer that, well, it pretty much broke mathematics for a while.
Oh, it was completely divisive. His answer wasn't just infinite, it was which one?
Right. He proposed that there isn't just one infinity. There's a whole hierarchy of them, an endless ladder of different quantifiable infinities.
And that's not philosophy, that's math. He developed the tools, these things called transfinite numbers, to actually measure and compare them. He treated a completed infinity as a real mathematical object you could work with.
And that's our mission for this deep dive. We're going to unpack that vision. We'll start with Cantor's original ideas, how he first distinguished between different infinite sizes.
Then we'll trace how that evolved. It gets very technical into modern set theory, large cardinals, these immense, almost unimaginable concepts.
But then we'll see how these abstract ideas have really surprising applications, how they help us understand the real number line, the very foundation of calculus.
And of course, we have to talk about the critiques, the pushback, the paradoxes, and the search for the absolute limits of what's logically possible.
Okay, so let's start there with that first fundamental conceptual leap. What was the big shift that allowed Cantor to even begin defining different infinities?
Well, for centuries, the standard view was called the potential infinite.
A potential infinite, what does that mean?
Think of it as a process. You're counting numbers, 1, 2, 3, and you can always add one more. Or a line that you can always extend. It's this idea of unlimitedly increasing.
So it's a process that never ends, but you never actually grasp the whole thing.
Exactly. You never get there. Cantor's radical move was to say, let's stop the process. Let's look at the completed infinite, the actual finished collection of all the numbers.
The set of all integers considered as a single object.
Precisely. He called them aggregates. And once you have an object, you can ask, how big is it? This is where he defined what he called its power, or what we now call its cardinal number.
So how do you measure an infinite set? You can't count it.
Don't. You compare it.
Yeah.
He set up this rule of equivalence. You take two sets, M and N, and if you can create a perfect one-to-one correspondence, a matching between their elements, they are equivalent.
The old matching rule. Every person gets a unique chair.
That's it. If there's a perfect match, no leftovers, then the two sets have the same cardinal number. They are the same size. For finite sets, this is, well, it's obvious.
Trivial.
Right. But for infinite sets, it became this incredibly powerful measuring stick. It was the tool that allowed him to start building his hierarchies.
So with that tool in hand, let's take those first steps. We begin with the smallest infinity, the one he named LF0.
Yes, Aleph dollars. He defined it as the cardinal number of the set of all finite numbers. It's the size of the counting numbers, 1, 2, 3, and so on.
And any set that has this size is called innumerable.
Innumerable, or countably infinite. The integers are innumerable. Even the rational numbers, all the fractions, are innumerable, which is a bit of a surprise to many people.
This is where the intuition really starts to break down, though, because these innumerable sets behave so strangely.
They do. Take the set of all positive integers. Now take just the even numbers. That's an infinite part of the original set.
You've thrown out half the numbers, the odd ones, so it has to be smaller.
But it's not. You can match every integer in it with the even number, 2. 1 matches with 2, 2 with 4, 3 with 6. A perfect one-to-one correspondence.
So they have the same size. Of the LF dollars, the part is the same size as the whole.
Exactly. That property, that an infinite set can be equivalent to a proper subset of itself, is one of the defining features of being infinite. It's just bizarre from our finite perspective.
I think I read that someone else had noticed this before Cantor.
Bolzano.
That's right, Bernard Bolzano had pointed it out. And Dedekind later used it as the very definition of an infinite set. But Cantor was the one who placed it inside this grand, systematic structure. Okay, so we have the size, Aleph dollars. But then Cantor also introduced another symbol, omega omega. Why do we need two different symbols if they both seem to refer to the set of integers?
That is the crucial question. It's the difference between size and structure, between quantity and order.
So omelos is how many, but the mega is how are they arranged?
Precisely. Omega is what he called the ordinal type. It represents a set of finite numbers arranged in their natural order. 1, then 2, then 3, and so on. Order matters.
And why does that distinction matter so much?
Because as soon as you introduce order, the rules of arithmetic get completely turned upside down. Specifically, addition is no longer commutative.
You mean 1 plus 2 doesn't equal 2 plus 1 anymore?
For transfinite ordinals, no. Let's take omega plus dollar versus $1 plus omega. Imagine omega as that ordered sequence of integers.
Okay, a line of numbers stretching out to infinity.
Right, to get to omega plus a dollar, you add a new element, let's call it f, at the very end of that infinite line. So now you have the whole sequence of integers, and then after all of them, you have f.
It has a final element. The original sequence didn't.
Exactly. So its structure is fundamentally different. That's the ordinal type omega plus de Boer. But now, what about $1 plus omega? Here, you place the new element f at the beginning of the sequence.
So you have f, then 1, 2, 3, and so on.
Yes. And if you just ignore that first element, what's left?
The original sequence. The structure of omega.
So $1 plus omega is structurally the same as omega itself, which means $1 plus omega equals omega. But omega plus 1 is something new, something larger.
Wow. Okay, that completely overthrows basic arithmetic intuition. The position of where you add something changes the result.
It confirmed for Cantor that these were a whole new species of number, and this ordinal structure was the key. It was the ladder he used to start climbing to higher and higher infinities.
Okay, so we had the first level of infinity, the alpha dollars, but the whole hierarchy just explodes with his next discovery, right? The uncountable.
This was his monumental 1873 paper. He proved that the set of all real numbers, all the points on a line segment, what we call the linear continuum, is not enumerable.
You can't make a list of them. You can't match them one-to-one with the integers.
Impossible. He proved it with his famous diagonal argument. No matter what list you make, you can always construct a new real number that isn't on it. This proved, for the first time, that there was an infinity that was strictly demonstrably larger than 12th draw.
And he gave that new size a name, the cardinal of the continuum, mathfrak.
Yes, mathfrak, which he later showed is equal to 2 Alice. And this discovery had some truly baffling geometric consequences.
This is the part I find hardest to get my head around.
Well, he showed that the number of points in a multidimensional space, say a 3D cube, is exactly the same as the number of points on a 1D line.
Wait, say that again? A solid cube has the same number of points as a tiny line segment.
The exact same cardinal number, mathfrak. He even showed it for an infinite dimensional space. In terms of the sheer number of points, dimension is relevant. It doesn't add any more points.
That's just wild. So how did he use the ordinals to build the ladder up from all the dollar to the next level, all the way?
He used that process we talked about. You start with omega, then you get omega plus the ball 1, omega plus 2, and so on. Eventually you reach a limit, which is 2 omega, then you keep going. This dialectic generation, as he called it, produces all the possible countable orderings.
You exhaust all the ways you can arrange a countable number of things.
Exactly. And the set of all of those countable ordinals, taken together, forms what he called the second number class.
And the size of that new collection must be bigger than countable.
It has to be. He proved it couldn't be put into a one-to-one correspondence with the integers, so its cardinal number must be the next one up. That's the definition of Olaf dollar.
The smallest uncountable cardinal.
Yes. And from there, you can define left to 2, left to 3, and so on, creating this beautiful linear hierarchy of ever larger transfinite cardinals.
But that structure immediately created what might be the most famous unsolved problem in mathematics.
The continuum hypothesis.
We have the size of the integers, left dollars. We have the size of the real numbers. Mathfrak, is there anything in between?
Or to put it formally, is mathfrak equal to LF2? Is it the very next rung on the ladder? Cantor was convinced it was. He spent decades of his life trying to prove it.
He couldn't.
He couldn't, and that failure set the stage for the entire direction of 20th century set theory.
Right, because after Cantor, the focus shifted. It became less about intuition and more about building a completely rigorous foundation. This was happening across mathematics, right?
Absolutely. Think of people like Cauchy and Weierstrass in analysis. They were trying to get rid of appeals to geometry or intuition. They wanted to build everything on the concept of number alone. Set theory needed that same level of logical exactitude, especially after paradoxes started showing up.
So the system that emerged was ZFC, Zermelo-Fraenkel set theory, with the axiom of choice. How does ZFC manage to avoid those paradoxes, like the set of all sets?
It uses something called the iterative conception. You don't assume all sets exist at once. You build the universe of sets in stages.
Level by level.
Level by level, indexed by the ordinals. You start with the empty set. Then at each stage, you form the power set of what you had before, the set of all possible subsets. This builds the hierarchy up, so a set is always built from sets that came before it. You can never form a set of all sets because you're always generating new, larger sets.
And that power set operation is what drives the whole thing upward, always creating bigger collections.
It is. And sitting right at the heart of this system is the very controversial axiom of choice, AC.
Which sounds so simple. If you have a bunch of boxes, you can take one thing out of each box.
For a finite number of boxes, it's a non-issue. But the axiom says you can do it even for an infinite collection of boxes simultaneously. It allows for this infinite selection without giving you a rule for how to choose.
And why was that so important? Why did they need it?
It turned out to be essential for proving all sorts of things, especially the well-ordering theorem, which says any set can be arranged into a well-ordered sequence. Cantor himself used it without realizing it.
But it caused a huge fight, didn't it? Especially in analysis.
A massive one. The classic example is from 1905. Giuseppe Vitali used the axiom of choice to construct a set of real numbers, the Vitali set, that is non-Lebesgue measurable.
Meaning you can't assign it a consistent length or size on the number line.
Correct. For analysts like Lebesgue, this was a monster. They believed every set you could reasonably define should have a measure. The fact that AC could create these pathological objects made them deeply suspicious of the whole axiom.
So ZFC provides the rules, but it leaves CH undecided and AC controversial. Which brings us to Gödel.
Right. If ZFC can't prove or disprove the continuum hypothesis, what can we say about it? Gödel's approach was brilliant. He constructed a kind of minimal, bare-bones version of the set theoretic universe. He called it the constructible universe, or L.
And what's special about L?
In the full universe V, sets can just exist. In L, a set is only included if it can be explicitly defined using sets from earlier stages. It's a universe built only from what you can describe with logical formulas.
A much tidier, more constrained reality?
Exactly. And Gödel proved two amazing things. First, that if ZFC is consistent, then ZFC plus the axiom VL is also consistent. And second, inside L, both the axiom of choice and the continuum hypothesis are true.
So that proved that CH is at least possible. It can't be disproven from the standard axioms.
That's the huge takeaway. It's a relative consistency proof. It showed that Cantor's hypothesis was logically compatible with the rest of set theory.
So why didn't everyone just adopt VL and call it a day?
Because L feels too restrictive to many mathematicians. It feels like it's missing things. And this was later formalized with the concept of transcendence over L. The idea is that our true universe, V, is probably much richer and more complex.
And the evidence for that is this thing called zero sharp. Zero sharp.
Yes. Zero-tag-Veller is a very technical statement, but conceptually, it's a kind of blueprint for the structure of L. If zero stack exists, it means the universe contains information that L cannot see or define. It proves that V is genuinely larger and more complex than L.
So the search was on for new axioms that could describe this richer universe. This is what Gödel suggested, right? Stronger and stronger axioms of infinity.
That's the genesis of the modern theory of large cardinals. These are axioms that postulate the existence of incredibly large infinities with very special properties.
They're like adding a new, more powerful engine to your logical system.
A good analogy. Each large cardinal axiom you add makes your theory stronger and allows you to prove more things. And they form a beautiful linear hierarchy of consistency strength.
Let's walk up the first few rungs of that ladder. The first one is the inaccessible cardinal.
An inaccessible cardinal, let's call it kappa, is a number so large that you can't reach it from below, using the standard operations of set theory. It's regular, meaning you can't build it by patching together a smaller number of smaller sets. And it's a strong limit, meaning the power set operation on anything smaller than it always results in something still smaller than it.
So it's a kind of island in the hierarchy. You
Yeah.
can't build a bridge to it.
A very good way to think of it. And its existence can't be proven in ZFC. It's a new assumption.
Okay, what's next? A measurable cardinal. That sounds even more abstract.
It's a huge leap in strength. A cardinal kappa is measurable if you can define a special kind of measure on all of its subsets. This measure is embodied by something called a kappa-complete ultrafilter.
Ultrafilter. In simple terms, what is that doing?
It's a way of definitively sorting all the subsets of kappa into two piles, large sets and small sets. The key property is kappa completeness. If you take any collection of fewer than kappa large sets and intersect them, the result is still large. This is an unbelievable closure property. It makes the cardinal immensely powerful.
And we know for sure it's stronger than an inaccessible.
Oh, yes. The least measurable cardinal is vastly larger than the first inaccessible. We're climbing the hierarchy fast.
Then you get to concepts like indescribable cardinals, which are defined by reflection properties. What is being reflected?
Imagine the universe of sets below an indescribable cardinal kappa, so the collection V kappa. The reflection property says that any statement you can make that's true about this entire collection, V kappa, must also be true in some smaller initial segment, V alpha, for some alpha less than kappa.
So the large structure is mirrored in a smaller structure below it. The part reflects the whole.
Exactly. The cardinal is so large and the universe below it is so robust that it's forced to contain smaller copies of its own reality. It's a sign of profound structural integrity and consistency.
So we have this ladder. Inaccessible, measurable, huge, super strong. Does it just go on forever? Is there a top?
There is a ceiling, a hard limit discovered by Kenneth Koonin, Koonin's inconsistency theorem. He proved that you cannot have an elementary embedding from the entire universe V back into itself.
An elementary embedding being a map that preserves all true statements.
Yes. The idea of the whole universe being perfectly mirrored within itself is just too strong. It leads to a logical contradiction within ZFC.
So that theorem defines the boundary of what's possible.
It defines the frontier. The cutting-edge research today involves axioms like the I0 to I3 hierarchy, which postulate embeddings that get tantalizingly close to that Koonin boundary without crossing it. It's about axiomatizing the largest, most powerful, consistent version of the universe we can imagine.
It's incredible that these ideas, which are so abstract they seem almost disconnected from reality, actually circle back and tell us something concrete about the real number line.
That's the magic of descriptive set theory. It's the bridge. Its whole job is to study the properties of definable sets of real numbers.
And specifically, their regularity properties.
What are those again? 3 basic signs of a well-behaved set. Is it Lebesgue measurable? Does it have a length? Does it have the Baire property? Is it topologically simple? And does it have the perfect set property?
What's the perfect set property?
It says that any infinite set of reals is either countable, so size of left dollars, or it contains a perfect subset, which guarantees its size as math refrac. Basically, it says there's nothing in between.
So it's a version of the continuum hypothesis for that specific set.
Exactly. And Cantor himself proved this for a simple class of sets, the closed sets. He showed that for any closed set of real numbers, CH is true.
So if CH were false, the counterexample would have to be a more complicated kind of set.
Right. And this is where Gödel's work with L threw a wrench in the works. Because under the assumption VL, he showed they're relatively simple, definable sets of reals, these Pyland-Alata-Mill sets, that are not well-behaved. They lack these regularity properties.
So in that minimal constructible universe, the real number line is kind of messy.
It's messy. ZFC alone isn't strong enough to guarantee that even simple sets have a length. And that's a problem for analysts.
So we need a stronger axiom. And this is where the large cardinals come back to the rescue.
They do. Robert Solovay proved a landmark result. If you assume the existence of just one inaccessible cardinal way up in the stratosphere of the hierarchy, that's enough to build a model of set theory where all definable sets of reals are well-behaved.
So the existence of a huge infinity far away can clean up the mess down here on the number line.
It shows that the structure of the continuum is directly tied to the consistency strength of the entire set theoretic universe. It's a profound connection. And the connection gets even stronger if you step outside of ZFC for a moment and consider the axiom of determinacy, AD.
Which comes from game theory, of all places.
Yes. AD states that for a certain class of infinite games where 2 players choose real numbers, one of the players must have a winning strategy. The game is determined. It's important to note that AD contradicts the axiom of choice.
So you have to pick one. You can't have both.
You can't. But the payoff for assuming AD is immense. It implies that every single set of real numbers is perfectly well-behaved. They all have the regularity properties.
All of them. No more non-measurable monsters.
None. The continuum becomes this beautifully structured, regular object. What's more, AD has powerful consequences for the cardinals themselves. It implies that omega-1, the very first uncountable cardinal, is actually measurable.
Wow. So determinacy in games forces the smallest uncountable number to have a property of a massive large cardinal. It injects that strength right down at the bottom of the hierarchy.
It does. It creates this incredibly rich and orderly picture, but at the cost of giving up the axiom of choice, which is so fundamental to other areas of mathematics.
This tension naturally leads us to the critics. Not everyone bought into Cantor's program.
Not at all. From the very beginning, There were mathematicians, the constructivists like Brouwer and Weil, who were deeply skeptical.
What was their main objection?
They rejected the whole idea of the actual infinite. For a constructivist, for something to exist mathematically, you have to be able to explicitly construct it. They rejected non-constructive proofs that say an object exists without telling you how to find it. The axiom of choice was their worst nightmare.
And some people even thought we should be looking for axioms that limit the hierarchy, not expand it.
That's right. Alfred Tarski actually proposed an axiom that would essentially forbid the existence of very large cardinals. He wanted to put a cap on the hierarchy.
Which was the complete opposite of the mainstream approach.
Completely. The dominant view in set theory was, and still is, to embrace the hierarchy, to find axioms that secure the existence of these cardinals and help us map out Cantor's absolute infinite in its entirety.
And what about the early paradoxes, like the set of all ordinals? How did the community deal with those logical landmines?
It forced them to be more careful, which is what led to the rigorous framework of ZFC. But in the early days, the response was sometimes just pragmatic. The set theorist, Schoenflies, famously declared that these paradoxes weren't really mathematics, they were philosophy.
A convenient way to sidestep the problem.
It was a way to keep working. Ultimately, the solution was to accept that while the absolute infinite might be a guiding philosophical concept, the mathematical universe had to be built within a strict, formal system to prevent it from collapsing.
So as we push towards that ultimate frontier, towards the Kunin boundary, what are the modern tools being used?
The primary tool is called iterated ultrapowers. We mentioned that a measurable cardinal gives you an ultrafilter, which you can use to create an elementary copy of the universe inside a model.
Right, a smaller version with the same truths.
The idea of iteration is to do this over and over again. You take the ultrapower of the ultrapower, and so on. This process allows mathematicians to construct models with incredibly complex large cardinals, like super strong or extendable cardinals, and to study their properties.
It's like building a mathematical microscope with ever-increasing magnification to probe the limits of consistency.
A perfect analogy. And that's what's needed to even define the concepts at the very top, like the I0 to I3 hierarchy. These axioms posit embeddings that are so powerful they come right up to the edge of what Kunin proved was impossible. They are our best attempt to describe the largest possible consistent universe.
And while that's happening at the very top, the axiom of determinacy gives us this amazingly detailed map of the lower levels.
An incredibly detailed map. Under AD, you can calculate the structure of the ordinal hierarchy with stunning precision. You can define what are called the projective ordinals.
And what did we learn about them?
We learned that under AD, this sequence of projective ordinals forms a strictly increasing sequence of measurable cardinals. For instance, delta $11 is just omega 1, but delta 44 is the omega plus 2/3 regular uncountable cardinal. It creates this predictable, rigid structure where none was known before.
And this all culminates in the most modern connection between the top and bottom of the hierarchy, which involves wooden cardinals.
Yes, wooden cardinals are another type of very large cardinal, and the connection is this. The existence of a certain number of wooden cardinals is both necessary and sufficient to guarantee the regularity properties for sets of reals at a certain level of complexity.
So if you want to prove that, say, all sigma 1404 sets are measurable.
You need to assume the existence of two wooden cardinals. If you want to go higher up the definability hierarchy, you need to assume more wooden cardinals exist.
That is just an astonishing link. To guarantee good behavior on the real number line, something so fundamental to analysis, you have to reach for these astronomically large infinities at the furthest edge of mathematical thought.
It suggests a deep unity. The stability of the continuum seems to be governed by the consistency and strength of the highest conceivable infinities. Cantor's ladder isn't just a collection of curiosities. Its rungs hold the entire structure up.
So we started with a simple question about how many numbers there are. We saw Cantor's answer blow the question wide open, leading to a hierarchy of infinities. This led to a search for new axioms, large cardinals, to settle questions like the continuum hypothesis. And now we see these abstract axioms have direct, almost healing effects on the real number line itself.
And it all comes back to an insight from Gödel. He said an axiom of infinity is a proposition that has a certain formal structure and, in addition, is true. The whole enterprise of large cardinals is a search for those truths. So the final question for you, the listener, is this. Given how stable this hierarchy is, how neatly these cardinals line up, how they solve problems in other areas of mathematics, does this prove that Cantor's absolute infinite is a real mathematical landscape we are discovering? Or are these just the most elegant, most consistent patterns our logical systems are capable of creating?